Hello everyone, Professor Dustin here, and this video is going to be a solution video to this whiteboard, which is called moving a couch. So you can see that this actually was from an exam. This is from spring 2018 exam. So this is very much like what you could easily see on an exam. And I've actually asked questions like this several other times. So it's a good whiteboard to go over to learn some things about how to combine Newton's laws and kinematics together in a situation which is, maybe not totally realistic, but is a model that we think of when we think about how physics can be applied in the real world. So I'm moving out of my apartment, but I've run out of space in the truck, so I'm going to drag the couch behind the truck as shown. We know what the mass of the truck is, what the mass of the couch is, 35 kilograms, and I guess I'll just call that M. And we can assume the rope between the truck and the couch is horizontal. That's good, so there's no angles with respect to the rope at all. And the coefficient of kinetic friction between the couch and the road is 0.15. So that is going to be my mu k. And we want to know how big is the force of friction between the road and the couch. That's part A. So we have to decide what approach, what principle we're going to use to solve this problem. We want to know what the force of friction is. We know things about the motion of the truck. So clearly we're going to do some kind of Newton's second law thing. So because we're going to do some kind of Newton's second law thing, the first thing I'm going to do is write down a free body diagram. So there's a free body diagram for this situation, starting with part A. You can see that I've got gravity and normal. Gravity because the couch has a mass, normal because it is sitting on some kind of surface. The tension force in the rope I've given by Ft, and then there's a backwards force Fk that's opposing the motion of the forward motion of the couch, and so friction is going to be trying to oppose that motion. It's implied that the truck is moving forwards, but we actually don't know whether it's accelerating or not, so I don't know the relative sizes of those two. So I've written it kind of like it's accelerating the right, towards the right, but we don't really know that yet. Okay, so we want to write down Newton's second law in both the x and y directions, which is there. So we have the tension force forwards and the kinetic friction force backwards. And I wrote MA because we don't know if the truck is accelerating yet. We don't know that much about this situation yet. So I'm just going to write MA, anticipation of later knowing something enough about the acceleration to solve that equation. In the y direction, we just have normal force and the force due to gravity. That equals 0 because we don't have to be told really that the couch is not accelerating in the y direction. We can tell by the situation that it's not accelerating in the y direction. Okay, but if we want to know what the force of friction is, we actually can't use Newton's second law because right here we're looking for that. We actually don't know what the acceleration is yet. So we can't use the x direction. But we do know what the normal force is from the y direction. So we can use the basic definition of the kinetic friction, which is that Fk is equal to mu k times the normal force. And now we know that the normal force is equal to the gravitational force because it's not accelerating in the y direction. So this is just going to be mu k mg. And then we can simply calculate that. So putting that into my calculator, I get 51.5 newtons. So basically using the definition of the force of friction and the fact that we know what the normal force is from Newton's second law to figure out what the kinetic friction force is. So part B of this problem says if the truck accelerates at half a meter per second, how much tension will be in the rope that is pulling the couch. Okay, great. So that's referring to the fact that now we can say that's what the acceleration is. That goes in there. We know what the kinetic friction force is. We've already calculated that. Friction, unlike kinetic friction, unlike static friction, takes only one value. It just is exactly whatever the normal force is times mu k, so we can calculate it independently. So then we're trying to ask what the tension force is. We're obviously just going to be solving Newton's first law in the y direction. So that's a restatement of Newton's second law in the x direction. Solve that for the tension. We get Ma plus Fk. Using the value of Fk in there, plug that into our calculator, and we get 25.8 newtons. So that's the current value of the tension if the truck has an acceleration of 0.5 meters per second. So part C of this problem says the maximum tension of the rope can take before it breaks is 200. Okay, so first it's good to acknowledge that we are below that 200. But since there is a limit on that rope, what is the maximum acceleration the truck can have before this happens? So that's basically going to be resolving the Newton's second law in the x direction for whatever acceleration it has when the tension force hits the maximum value. So that's again a restatement of Newton's second law in the x direction. I'm just going to say I want the tension force if the tension force hits its maximum. So of course this is not like the same equation as here because this is for any given acceleration tells me what the tension is. For this one I want to say if the tension is maximized, then what acceleration does the truck have? That's kind of like I'm inside the truck. What acceleration can I give the truck and still be assured that the couch is going to be attached and dragging to my new apartment? So it's just a matter of solving for the acceleration. That's a pretty easy process because we just divide by m. So write Ft max minus the kinetic friction divided by the mass. And again, with the kinetic friction does not change as you change the motion of the object. As long as you are still moving and still under the influence of kinetic friction, you will always get the same value for the kinetic friction. Okay, so if I calculate this, in my calculator I get 4.24 meters per second squared. That's a pretty healthy acceleration, right? That's half the gravitational acceleration. I mean, basically, I guess I don't know offhand what the acceleration of cars and trucks have, but you'd think it would be like less than a tenth of gravitational acceleration because you might feel pressed into your seat a little bit when you accelerate in your car, but you don't really feel that in an extreme manner like if you were in a race car or something. So that seems very safe. It seems to me like there's almost no chance of this truck actually hitting that acceleration. So whatever I chose for my rope to carry this couch seems to be very safe, and it's not likely that I'm going to break the rope by getting to that acceleration. But that's the maximum right there that I can go. Okay, great. So this has been a relatively simple problem, but a combination. It's not really a combination of kinematics and Newton's laws because we didn't use any kinematics. It's really about Newton's laws and friction, and then also acknowledging that, okay, we can just do simple solutions like A and B, but also we can do slightly more interesting things like saying, like, under what physical conditions will the Newton's laws that we've set up for this, will this break, will this still work, such as the natural limits that we all know about on things like ropes and cars and other things like that. So that's what I was thinking when I created this problem, is just like, oh, here's some simple things we've done before, but actually we can like think seriously about what if I actually tried to do this thing out on the road. Okay, great. So this has been a solution to moving a couch. Hope it has been helpful, and I will see you guys later.